Thank you all for being here. Can you hear me well at the back? I'm totally okay with taking my mask off. I just was sitting to this lady that was coughing for 8 hours straight. So just in case, I don't want to basically anyone blaming me for that here. Anyway, the perils of long flights, I guess, nowadays. With that, onto the talk. Basically, I want to give a little bit of a higher level perspective coming after this really exciting, and deep talk into the internals of networking interfaces and networking and NICs about what can we actually do with them. Clearly, the data centers basically are becoming more complex. Their topology is becoming more interesting. Clearly, we need to start becoming aware of how things are processed and how traffic flows in the network. We also have a limited visibility problem. No cloud provider really wants to actually tell us a lot about what happens behind the scenes, so to speak, but we can infer many interesting things. But again, what is interesting from a data management perspective here? And I will point out a few things that, in my opinion, stand out as very interesting questions. And much to my surprise, I have not seen anybody really try to tackle them basically head first. And in part of what I'm trying to do here is, again, I would love to actually plant the right questions and hopefully hear back what you think the answer should be. Starting, again, what does it mean? Again, what does a modern network look like? Things started really simple. I have a few computers in my lab. I connect them all to one switch. That is fantastic. Everybody has this basically fixed latency to everywhere. I have full bandwidth from every node to every node. And you might laugh at that because this is a really trivial topology. Yet it turns out this is the predominant topology every query processing engine, every cost model today thinks the network is. It is a flat, uniform network where I have fixed latency links and full bandwidth everywhere. Of course, what happens eventually, you need to get another rack. Now things start to look not so uniform. And very quickly, you have a tree. That is, you connect separate racks with those basically links. And usually those are slower. A metric people often cite is what is the oversubscription rate. That is, how many times less bandwidth do you have up here compared to the level here, and from here to the top level. A very common oversubscription ratio, as I'm hearing, sits below 2 or 3 sometimes. That is, you would expect to have 2 or 3 times less bandwidth as you go up. This makes, in some sense, cross data center communication slower if you have an architecture like that. Of course, the issue here is all the way that this top node, this is not a small switch, mind you. That switch is probably taller than I am. It has 600 plus ports. But that will determine your overall speed. And that can be a problem. There are ways to actually avoid this single bottleneck, but you need to invest a lot more in your network. What can you do here? You can actually start going towards what people refer to as high-radix topologies. You can look and now create another path for these two to communicate. That will give you more bandwidth at the top level. You can actually keep adding there. You can apply exactly the same trick at this level. And now you can replicate that as well. And as you can see, the links may look a lot messier, but now you can see that you have more bandwidth to any destination in your network. There's also some redundancy in the sense that here you have basically 2 ways out in every case. Those start approaching what you may have seen as CLOS topologies, close, leaves and spines. And you can make this scalable, but the point is that it becomes a lot more expensive to do so. Here's again, this is from a slightly older system. This was a Cray basically system at Lawrence Berkeley, where you see exactly the same pattern repeated at different levels, all the way from cabinets down to the chassis, down to the individual blades, but still the overall same topology. And the main issue here is that common patterns we love to use, like shuffling, triggering, and all-to-all repartitioning, simply do not scale. Here I'm plotting number of CPU cores, and as I go into the thousands and hundreds of thousands, this is from a slightly older system, basically, I go from the rated throughput of 4 gigabytes per second all the way down to nothing. Why? The network is super fast. I just use it in this extremely inefficient way. There's another aspect here outside of scale that I want to call out, And there's no better example than the smart NICs that were discussed extensively in the previous talk, which goes back to basically the fact that the topology is becoming heterogeneous. Here's an example. This is the Bluefield, basically one DPU that I will be showing. The idea is that whereas before you had a direct link between two NICs, now you will add those smart NICs with some memory and compute capability. But this suddenly creates a very heterogeneous, basically, looking network. Here's why. At least, in the first implementation of the Bluefields, one issue is that the smart NIC is really sitting as a separate ARM core connecting to the PCI Express bus. That is basically effectively looking not as something that is inside here, but you can think more of it as something that is attached to the NIC here. In fact, I would suspect if I were to cut open the die and actually see the packaging, I would see two completely separate things side by side, right? That is what this first version suggests. But here's an interesting, basically, latency metric. I'm now doing a simple RDMA write. Note the terminology here. As in the previous lecture, I have an initiator and the target because I will show an RDMA read on the next slide. I don't want to confuse anyone. If I start and initiate at a smart NIC, I can go across the network. This is only a single hop to the other NIC in 2.3 microseconds. I can go to the host CPU in 1.6. That should tell you a lot about, if you like, the relative cost of actually invoking the IBV stack from this slow and low-powered ARM, and what fraction of it is really spent on the network versus over the local PCI Express bus to memory and back, right? So we see this, if you like, difference. What is even more striking is because of that, reads are asymmetric as well. If I read and basically start from one side, I will read in 3.3 microseconds. If I read starting from the other side, I would actually read in 2. So here you have what looks like and is advertised like a bidirectional link that can run at full speed from both sides. Yet, because of this compute, basically, mismatch, doing it from one side is slower than doing it from the other. So that is another interesting aspect, that although we like to think of the world as having full bandwidth and equal latency on both sides, new components in the network point to the fact that maybe this is an assumption we want to change, right? And of course, finally, something that was not mentioned before, it turns out this small ARM core is basically has a very weak memory connection. We could barely get 12 gigabytes per second using a common splash benchmark. That is just local memory speed compared to the 100 gigabytes per second we get from the local CPU. That is another aspect of heterogeneity as we look at this topology, right? And you can recall, going back to the previous talk, basically, what does it imply for your processing if you can talk to memory at 1/10 of the speed that you can talk to your memory on the other side? So with that, I think it is sufficiently clear that we need to be thinking. Please go ahead.
Ask a question. So what is that good for then?
Does
this deposit the memory and the data into the CPU and I have 10 times more bandwidth?
Well, I cannot answer conclusively this question. I would like, again, to let the answer come, but I have it as a paperweight on my desk. So that is one use I have found for it. It's not connected to anything, but it keeps my papers basically stable before the wind blows them. So that is at least one use. But you're right, the specific design and the fact that they connected this to this really slow bus, right, makes one question in some sense how capable this is really for data processing, right? Anyway, at least the first version of it, which I have tested. But yes, I think you will find many others with the same sentiment that really question in what part of the space this fits. So with that, continuing. So what I would argue is perhaps one approach to think about it. We need to start thinking about the topology a lot more, right? So in many ways, what I'm trying to convince here is that we can think of scale in all those negative terms, that things are slower, it becomes more expensive, it costs more energy. But there's also some hidden power, if you like, within that. That is, perhaps we can harness a topological structure. And by that, I refer to in a broad sense of either a network structure or basically a compute and bandwidth structure, or even perhaps some topological information from the problem itself. That is things like the similarity of different basically sets of data on different nodes can be thought of as, again, vectors in a topological space as well. So in this theoretical view of topology, can perhaps give us information to now process things a lot more efficiently, right? And that is the main thesis here. So in some sense, perhaps understanding the topology is the key to unlock some hidden power of scale, right? That allows us to scale a lot more efficiently than we're currently thinking about. And of course, that will need to bridge theory and practice, starting from, again, the foundations of what, computation cost means, of what is more important. Is it one cycle of compute or transferring one byte? All the way to how do we make algorithms built on those models practical. And I will just show, again, some of the work we have done, trying to, again, highlight the main interesting parts here for hopefully your ideas to plug in and take it further. So first thing, we need to have now a model of data movement, right? The cost is no longer how many floating point instructions I can execute per second and how many floating point instructions do we take. The real cost now is what it takes to move the data. So here's a simplified view of, again, what I would refer to as an arbitrary topology. I have designated compute nodes. Those are in dark. There are nodes that only do routing, which are in white. And we can add some compute as well if we basically change the model a little bit. But for now, let's just assume that compute only happens on the edge, just to keep things simple. The role of those nodes is to store data and perform computation. And I now refer to this in a very theoretic manner, as in I have a memory of, say, some tuples, of a certain basically number of tuples, and I actually perform computation, think of it as a sum in basically a fixed time. Let's see an example. Sorry, and I forgot to mention, each link now is associated with a bandwidth. That is how many things it can pass through one cycle of the system. And even with that really basic model, it turns out I can actually reason about costs in a very different way. Let me give an example here. And the main thing here is basically that, again, input data are distributed across the compute nodes, algorithms proceed in sequential rounds. And again, on every basically round, I move something and I compute something. The idea here is that now the cost in this new model is actually quantified not by the computation cost, but actually how long does it take to transfer the data over the slowest link in this graph. Let's see an example, perhaps, to understand what is going on here. Take the really simple case of an aggregation, okay? So I start, my values are T0, T1, T2. I want to collect the final output here at V3. I can run a really trivial program that basically says, everyone send their tuple to V3. Under the previous model, this will be a one basically step computation. But if everybody sends, and you can map the flows here, the issue will be crossing this link. This only has a capacity of 1, yet I have to transmit 3 items, T0, T1, T2. Hence, that is the most bottleneck link. Going back to my cost model in the previous slide, this is quite slow indeed. My cost model says that the cost of the round is where the maximum cost is. Hence, that determines the entire cost. So here, I will avoid basically those slide switches. Cost is 3. Why? Because 3 items have to cross basically a one item link. This takes cost of 3. Can I do better? Turns out I can. This is a simple version of, again, a max flow problem. Here's a separate strategy. I will be sending T1 directly to the destination, and V0 will send its contents to V2. Now, if you look at the links here, those can proceed basically, and here I have a link bandwidth of 2. Hence, those can reach the destination in a cost of 1 only. And I will end here. Now, after performing the computation here locally, I can take this result and send it down. That would now cost me only 2 in total. So this really simple and naive model of basically data movement can already point to perhaps a slightly different way to do aggregation, right? That is, I avoid pushing the full product all the way at the end, and I go somewhere else, compute a partial product, and then basically send it, such as to avoid making this slow incoming link a bottleneck. We will get back to this insight a little later, where I will show you an example where we actually saw an application trigger exactly this bottleneck in a massive aggregation at scale. So now taking a little bit of a theoretical detour here, it turns out that computing an optimal aggregation scheme over this model is NP hard. And thus we need to seek an efficient approximation algorithm for that. That is, we want to basically go and approach the optimal within at most a constant factor, which is always the strongest guarantee theory can provide. So efficient means you would like something that's computed in polynomial, or at least basically near linear time. And we want to keep the number of rounds small, because in theory, we can think about those rounds as having no cost. In practice, if you have too many rounds of that, just basically navigating through those rounds can actually eat up significant amount of time. So ideally, we don't want those communication, if you like, plans to be too deep and have too many dependencies. And finally, I want each step to be able to be computed completely locally without really requiring any global coordination on information sharing. So the good news here is that for some problems, which I would argue are the building blocks for interesting operations like joins, we can actually prove under this model that we can find almost optimal algorithms. Two important caveats, though. This is where we had done in pods, I think published a year ago now. Our results only hold for symmetric tree topologies, right? So if there is asymmetry, as I showed before, we are not sure if the results hold. If your network is not a tree, we are pretty sure the results do not hold, right? Please.
So which means failures do not work.
Sorry?
Failures are not supported. Switch only failures.
Yes, we haven't even approached that, yes. But indeed, yes, because if you have only a single path, then this will terminate your computation. So yes, this is actually a very big limitation in practice. It goes back to the ordering that many people take for granted, because it works when I connect card A to card B. If now A is in one part of the and B is on the other side, A to B and ordering between them may not work. More on that on the second part. But the theoretical results basically are limited to this particular topological structure, basically symmetric trees, and that is perhaps one of the biggest limitations. What do I mean by optimal? Mind you, this is slightly different than the optimality in the P or NP world, where you focus on computation. I refer to optimality as in basically what can you do given the initial data distribution sizes, right? Note, I'm not assuming knowledge of the input distribution, only of its size. That is, I will know somehow that at least how much data every node in this compute network will have, okay? But under those two basically assumptions, we can actually prove interesting things. Now, let me sketch how the algorithms will go. I'm not sure if I will go into the details. It's a more of a theoretical argument here, but starting from the set intersection, the main idea, again, now to compute the intersection of two sets. What is the lower bound here? This turns out to be fairly easy to prove, going back to, if you like, an argument in communication theory. That is, it doesn't really matter what is in here. I can actually basically point out that either A needs to send all of its data to B, or B basically needs to send all of its data to A, and hence I can use basically, again, communication theory and what it takes to actually exchange that many bits of information and arrive at a lower bound, right? Which is actually fairly straightforward to do so. Of course, the interesting problem is if I can approach this lower bound with basically a practical algorithm, which basically we believe we can. How do we go about basically this? It's quite simple. We can actually think of now two subsets of the network, A and B. We can point out that to compute an intersection, any data has to go through this link, the slower link of a tree topology. Thus, I can take the minimum of basically the sizes and the number of nodes on the subsets A and B. And then I can go all over this and I can obtain the lower bound. I won't tire you here with the precise mathematics. You can go back to the pods paper and refer to our wonderful collection of theorems and proofs if that is what you want to do this morning. Please.
Couldn't I compress the sets into some more efficient representation and detail all about it? Like if I, for example, figure out that every other element is set in set A, I could just encode that and send that as a code.
Indeed.
From overall complexity side, and this is a Shannon argument, right?
Correct. It's a little bit of perhaps of the mismatch is a little bit on a theoretical formulation. I am assuming here a proper set. Okay, I won't bother going back. I am assuming it a set as in the basically the mathematical notation. Hence, compressing, I will never see a duplicate key, for example, right? Anyway, so I do make those assumptions. So set intersection only pertains in some sense to really identifying if there's a common element in this, right? Could I compress it by, again, removing redundant bits? Possibly. On the other hand, I can do this thing.
Algorithmic compression. If every second element is set, I can just state that as an algorithmic fact. I
see your point. I see your point.
But okay, let's move on.
Yeah, to be honest, I have not. Let's start offline. We had a few thoughts, but anyway, it did not this did not appear. We will talk more offline. Yes, but this is again one other interesting aspect in some sense. If we can, in general, have a generating function that could produce a subsequence of basically anything, right? It's one of the things we thought about. In general, we dismiss this as not being practical because our algorithm starts from the assumption that we know only the size of the data. We have no information even of its distribution, let alone of its ordering, right? So anyway, of course, this is set intersection, so ordering doesn't matter, but it will matter for the sorting case, which I will show next. Anyway, but definitely, lots of room for improvement, right? Don't make this come across like a conclusive result. We have only found, again, one place, one tiny spot in an entire ocean of uncertainty where we can actually prove something that we thought was non-trivial. And thankfully, the pods reviewers agreed with us. I can give you the precise algorithm in its theoretical formulation, but we have an example of that later with aggregation. So in the interest of time, I will just quickly skip that part since this is really an algorithmic, basically, question. But suffice it to say, you have to basically, in some sense, look at all the cases of how RNS can be distributed, and then apply the same idea basically at different levels. And the final result here is that we can actually have a one-round algorithm that computes this intersection within this log V log n factor of the optimal solution with high probability, right? Again, given the assumptions we had before. Interestingly enough, the actual bandwidth costs are not used in the scheduling algorithm, a finding which surprised us as well. And however, the topology does affect the choice of the partitioning, basically, in the algorithm, right? That is where, in some sense, that is factored in. The roots of this basically observation are actually quite profound, and I will basically leave with a homework question at the end, because it is very tempting to try to adjust the problem a little bit to get a lot better in terms of algorithmic results. Please, a question.
And we reduced the volume down previously, like if you send balloon filters to other sites with high probability, I could get minimum communication cost of the intersection side because I send like it's to the other side.
Correct, but here we're not looking for here we are not looking for basically the size of the intersection. We are looking for the actual result, right?
But with high probability, I could potentially compute the intersection with communication complexity side of the intersection, because I can communicate to the other side how to reduce its own side in a sense before communicating it with it.
Correct, but this is now what you're communicating across, right? Would actually be basically a function of the data size, right? Yeah.
Like I could say B can say to A, here's like a small data structure that you can use to, in a sense, filter out all elements that I don't contain, and then.
So in essence, you're discussing basically about not shipping in some sense a sketch of the data instead of the actual data across, and only basically taking that as basically, and as you.
Before you do the intersection, you can in a sense pre-filter most of the elements.
Indeed.
And then in both sides you have almost only the intersection, which you then you use your algorithm to in a sense, further intersect. But like in this scenario, if you're looking at the complexity as the type probability, then the lower bound we should be looking at should be the intersection size, not the data set size, right?
Right, but in your algorithm to compute the final result, you would still need to ship basically the data at the end, right? And that is what, in some sense, this observes, right? Mind you, this is again, this is the big O basically world, right? Yeah.
Like if the intersection is empty,
right?
Then you send sketches.
And this is trivial, yes.
And there are no intersection,
Mm-hmm.
and then my communication cost is almost zero.
Correct.
So the lower bound is not the data set size, but rather the intersection size, which is likely much smaller than the data set size.
Indeed, but maybe the notion of the lower bound here basically is slightly different. That in that sense, you are in essence you're now looking at the actual elements of the data, right? Again, this goes back to the definition, right? You're basically the argument you just made holds. But you're not using you're telling me this can be basically, the lower bound can be broken because you know a priori that the results will not match, right? But if I give you only the numbers, because only the size is what I assume to be known, which we found this to be a more realistic abstraction, right? Then with respect to just knowing the number, right? I do believe it's much harder to do than that, right? Yeah, but in some sense, you assume more knowledge than our model, right? Yeah, that is all I'm pointing out, that you assume basically the ability to run some function over the input and pass that, which again, I'm not saying it's an unrealistic assumption, right? That is a very good, in fact, approach to actually strengthen this work further, right? But you're assuming a slightly stronger model than we started with, right? That is your ability to sketch something and use that as the input, right? And the starting point, right? I start from a lower level where I only assume that I know the size. And as you know from database, basically, even knowing the size in many cases, people who dismiss as impractical, right? Because if the size is the output of some previous computation, right? How can I even know the size? It's cardinal estimation. It's impossibly hard, right? Your point is well taken, that in some sense, if I knew more about the distribution or had the ability to evaluate a function on it and actually return something, right? Then I could in fact do much better, right? Indeed. This is in fact precisely what we leverage in the aggregation optimization in practice, which I will show afterwards, right? Unfortunately, we don't have data on that, largely because it is a little hard to formally basically introduce what is allowed to do then, right? Let alone that the notion of going through all the data to compute a function, a user-defined function, could come across a little bit as cheating because, what are the bounds, right? Is pre-computing the entire result all right? Bloom filter, how big is the Bloom filter, right? Is it really tiny? Am I looking at 1,000 values? Or my Bloom filter is 1,000,000 values, right? Anyway, those practical basically tunings would give us very different practical results, yet theoretically, are trivial because they're just constants and they're hidden away, right? But the point you make is a good one, that we can probably do better than that, right? Assuming more knowledge. I have no idea how those results would look like. I'm not even sure if, again, the lower bounds hold or, what are the lower bounds in those cases, right? Yeah, but again, back to this basically difference, I want to stress that, we start assuming that we cannot do that, right? All we know is how much data we expect to send out, right? And that is our starting point. Yeah. One thing you could do is you could encode that possibly as a step in the algorithm, right? If you were to do so, then I would argue that that step is basically what would take you basically and push you to that. That is, if you now compare the sum of the two, I'm pretty sure the theoretical basically result would turn out there, right? Anyway, thank you for this, because it's really important to understand in some sense what is the constraint here when I say optimality, right? That's what I threw those up at first, because if you change any assumption in many admittedly realistic ways, results no longer hold, right? Continuing, please.
Yeah, perfect. Regarding like what we know, what we don't know, when we're considering these. So eventually, if we do this in the full system,
correct.
Can we get something from the optimizer first?
Yeah, that is a great question. That's why we assume basically only data sizes. We figured that cardinality estimation would at least give us that. Can we do better? In many cases, yes. We can, for example, assume, I think, easily min-max, right? Yeah, this is one more level of information. We can assume full sketches, as we proposed, right? Bloom filters and other types, right? Actually, I would point you to a local colleague, Xiao, did a lot of this work actually. So Yes, exactly. So, she's the one who did all the mathematical heavy lifting here, because I claim no competence basically with those, theoretical tools. So anyway, again, just an FYI and everyone in the audience, it's not me who did all of this work. It's the sum of all the people, I work with and my students whose work I'm really presenting here. So, so continuing here, same for Cartesian product. A very similar result, again, that now we have a constant factor, basically by following basically the same idea. And this time we can actually, we will use both the distribution and the bandwidth of the links in the algorithm. The assumption here is now that the sizes of R and S are equal. It is way more complicated if we relax this assumption and we no longer assume that the sizes of basically the two tables that we do Cartesian product on basically are not the same. Practically, I'm not sure if this is a big issue in the sense that, let's say the worst case for Cartesian product is if you take a big and a big data set, right? So 1 billion times 1 billion, that is a really impossible case. If those are different, then this probably means that one is much smaller than the other. So I think, that is in general an easier case to handle in practice. So I'm personally, I wasn't too worried about putting this assumption there. We also have a result for sorting. This time we only have one set, R. We assume the input is basically arbitrarily distributed across the compute nodes. And we aim to distribute R in basically an ordered way. And the main, again, assumption here is take any node pairs I and J, all the data in the first node will be no larger than on node Vj, right? So that is, in some sense, I can follow the network in some order and find out basically the ordered result in the end. The key result is basically that, again, we can now do a 4-round sort and again, stay still within this constant factor with the optimal solution with high probability, given the assumptions we have basically stated up front, right? And anyway, it turns out here basically, again, the initial data distribution affects basically the algorithm, but the actual bandwidth costs themselves, are not actually used in that. Now, switching over from the realm of, again, theory and proving what is possible to the more interesting question of, can we make any of that work in practice? And I will show a few examples here. One is a case where the parallel join with network interference. I will also show a join and oversubscribed tree topology, and finally a case for parallel aggregation, for which I have a few more slides. So the example here is really simple. Assume you have, this was the uniform topology with one exception, one link, I don't know, some other VM is collocated on V2, it's downloading a big movie. This bandwidth basically here is impacted. You will get a lot less basically bandwidth on this link. How do I process a join then? Well, in the current setting, assuming uniform topology, everybody gets equal work, right? That would actually be really slow because you guessed it, the problem would be sending the data over this link. Can I do better? Of course, and I think that should be fairly intuitive. I can actually now change my hashing and basically distribute data proportionally, not to the compute capability, which I assume to be the same, but actually to the network capability of every system, right? So if I could somehow understand how much is this interference costing me out of this link, I could adjust my hashing to allocate proportionally less items to it, right? So that in the end, I'm actually ending up with a balanced system. That is the main insight, to which I think, everybody would nod their heads to as a practical thing. Turns out the model can actually produce that and predict this. And basically, it maps pretty well to what we would see in practice when we did this experiment. The model basically predicts the dashed red line for this interference oblivious join and how would it get worse as the performance degradation of the link gets worse. What would I do if I, again, assign weights in this topologically aware manner such that each node processes data proportional not to its compute, but to its current network capability? And you will see that the actual practical observations align very well with what this theoretical model told us and predicted in the first place. And it turns out here, basically, and perhaps a surprising result, which opens up a new, in some sense, question in those fields, a completely randomized algorithm turns out to be surprisingly effective, that in some sense makes those decisions basically of what to send where completely at random, which again, we are not even sure theoretically why this is so, but this has opened an interesting line of question of whether, randomized algorithms actually can hold the key perhaps to understanding this better, right? which is a little bit counterintuitive as to why a random decision would be better than the informed decision. But anyway, that is more for a theoretical basic consideration at this stage. Continuing, remember this oversubscribed tree topology where there was a slower link to connect two parts of the system I showed. Well, here I'm assuming a join between R and S. I'm assuming R is smaller than S. Each node, which are stacked on the left and the right, has only a fraction. It's basically equal fraction of the input, right? If I were to evaluate this as a hash join today, right, being oblivious to the fact that this is slower, I would actually basically hash the smaller, basically, hash basically one within the group. Sorry, let me take a step back here. So if I were to evaluate this using the current standards today, I would build a hash table on the smaller side, R. I would then direct basically the larger side and stream it to the appropriate destination, right? As you guessed it, the bottleneck will become this part here, data that crosses basically through this slow link. How can I do better? Well, here's what I could do. I could actually basically now keep S within the group. That is, I can avoid sending the large table over this slow network and instead take R and redistribute within and replicate across at the same time. That is, what I would do here is I would take basically, instead of just taking an R tuple and sending it to the destination, I would send it to one destination within and I will make a copy and send it out. In this way, what do I gain? I do send R out once over the slow link, but I'm not touching S. That is, I'm touching it locally, but I'm not touching it and sending it across a slow link, which turns out to basically have a benefit, right? I have results for this basically for, again, a case of basically, a commercial data center, but it's tantalizing to approach this topological problem. Again, think of the case of a NUMA node. Is maybe the answer to those basically partitioned or not partitioned join papers, of which I've written one basically a long time back, is perhaps then the answer that if those two are now NUMA nodes, I can hash within a group, but also create a copy of the hash table on the other side, and hence, avoid the slow link between NUMA nodes? An interesting experiment to try for sure. I have no data on that, right? But the theoretical cost model would suggest that, right? That maybe a faster way to run a non-partitioned hash join is to actually basically create now as many copies of the hash table as NUMA nodes, just to avoid basically sending the bigger S table across, right? And now you can see how this simple theoretical model can perhaps lead us to consider algorithms that at first didn't seem to make a lot of sense, right? The practical result here, again, model predictions, one too many. Modeling predictions here, again, dashed lines, dots basically is what we get. It turns out that basically this can go, the topology aware join can basically be at 2.5 times faster than uniform hashing. The other alternative is basically broadcast join, but this gets expensive very, very quickly, as is well known in practice, right? So that basically on the joins. I want to take a little longer and basically go through a case of aggregation that we saw from an interesting basically science data set. And with that, I will conclude this topology part. So we came across this interesting MODIS data set. It is a set of basically satellite images that make basically climate observations. Satellites go around the Earth. They take pictures of an area. This is, say, picture one. It gets sent as a single JPEG file to some node in your big cluster. That's a parallel file system storing that, so it does a good job of striping things to every node. 5 minutes later, satellite sends a new image. This goes somewhere else. You give it more time, more images, and more images, and more images as this passes over places in the Earth, on the Earth, and so on and so forth. The animation here is really slow. What is the net outcome of that? You end up piling up information. Yet, because of the nature of this collection process, here's an interesting observation. Ask any question you want about a single location. This is Columbus, Ohio, where Ohio State is. The answer to your question is going to be found only in whatever files intersected that particular location. And in this case, I've highlighted those three. So now, in essence, what you have here is you need to look at the raw data to actually find out what the answer is, say what's the average temperature of the day or what's the average sky coverage. But this is really a needle in a haystack. That is, you want to aggregate, sure, but you're really doing this aggregation over basically a very small set of keys, sorry, a very large set of keys, but a very small set of values, right? That is this high cardinality aggregation that every database is really scared of because they usually haven't implemented well. Can I map it into a relational problem? Sure, here's a relational analogy. If I take latitude and longitude as a key, I have observations for different locations stored as different values. I want to basically run a good old-fashioned group by over the key and compute my aggregate over those few values. This is really not a relational problem in the sense that the values may need some image processing, it may be some small kernel I need to run and so on. So maybe the computation that computes the aggregate cannot be expressed in SQL, but the main pattern is the same. So what is the issue here? Well, obviously, if I were to now assign these basically different locations, I would actually now be pushed at the end to collect those on my destination nodes. They will be overwhelmed because their inbound link is going to collect all the data that come through. How can I do better? Remember, this all-to-all pattern does not scale, right? How we can do better here? We can adopt an idea from sketching. Now, on the practical side, note I'm making a slightly stronger, basically, assumption here. First, I'm showing you the actual sets, which I did not know before. But if I were to do it naively, send everything to destination, all those 9 keys need to go and reach a final destination. The final cost would be 9. There's a faster algorithm here, which we refer to GRASP. It turns out to be SSE hard. SSE is this favorite approximation problem that is known to be basically, it's assumed to basically be hard to approximate, and people show the hardness over that. It's a little bit like the NP problem for the approximate world. And GRASP is a heuristic that we will basically build this aggregation tree based on data similarity. How would this go? Observe here, the keys I showed you are not random, right? In fact, 3 and 4 collect the same set of keys. 2 has a different set of keys. How can I take advantage of that? Again, if I were to aggregate data from nodes 3 and 4, right, the partial result coming out would be basically less than any other possible aggregation schedule here. So over this aggregation, if you like, now the topological structure, this network has no interesting topology. The topological structure for this problem comes from the data similarity, right? In some sense, I can encode the possible similarities on basically a topological space, and that is where the topological aspect comes in. But by doing that, I can actually complete this aggregation by transmitting 6, basically paying 6 units overall. How? I'm transmitting and draining the network first this way, then I'm taking the ABC keys and pushing them up the final destination, right? And this turns out to only involve pairwise communication, which can scale really, really well. What is the main idea here? I won't have time to go into the details. I start by, again, looking at those keys. I cannot move all the keys around. That's hard. But I can compute min hashes that are tiny enough to be sent over a single packet. That is, they're under 1 kilobyte. And they can all be collected, basically, by the destination, which will then determine and estimate the size of every possible intersection and go through a really simple, greedy algorithm, trying to, in some sense, minimize the projected data transfer cost by understanding, again, the cost of through the sketches, the cost of transmitting the intermediate data at every single step. Happy to point you to the paper for details. But this turns out to work really well in the cases where you have, again, an aggregation over basically many groups where each group has very few values in it, right? In this example I showed you, basically, we do 3 times better than repartitioning and 2 times better over approaches that only look at how to do this well and look at the network only and ignore the data, right? So here, I just want to point out and use this result as an example of that even in cases where there appears to be no interesting network structure, this was assumed over a uniform network of 4 nodes, there may be some topological aspect if you look at actual data distributions and their similarities in a vector space, right? Which we thought was quite interesting. With that, some open-ended questions that I want to pose, and I'm happy to discuss answers, although I have a flight that's leaving soon, so I would appreciate answers via email. I showed explicit topologies here. Nothing like that exists in the cloud. What can I do? This brings the interesting question of topology discovery, right? Turns out, if I am willing to assume, and again, that's an assumption clearly, a form of basically a tree as the underlying network, I can do basically discovery through a fairly automated process, right? We haven't talked about this result a lot, but this turns out to go back to, again, well-known ways to actually basically fold the metric space and everything, but it turns out to be easy to do in practice. An open question there, even within that subproblem, if now my structure is a mesh, right? Or any other structure really, can the same results hold? Not sure. What am I losing if I assume, if my network is a mesh, but I assume it's a tree? Not sure either, but those are very interesting open questions. What is the real overhead of scheduling and communication is another, right? I don't want to take one data center to run an optimization problem to tell me how to transmit data on another data center, right? So I want to do something that's really lightweight, really efficient, and hopefully saves me data most of the time, right? But it doesn't make the problem too complex. An open question, I propose a data movement cost model. There's always computation, right? The class example is, again, smartening doing linear algebra. If that's what you do, then I'm sorry, but our data movement cost model will not be accurate at all. You will be blocked at communication, and those two impact one another. Can we somehow hide it and embed it perhaps in the algorithm, in the topological structure? That's another interesting question we haven't really thought about. Another tantalizing question, a constraint in many of the algorithms we actually show is that we assume that the output needs to be deposited under a certain partitioning function at the end. It would make life a lot easier for the algorithms if I can actually deposit data and then tell you what was the partitioning function I ended up picking, right? Which, at first sounded ridiculous, but if you think about it, there's no real need why the partitioning function that was chosen cannot come in after the fact for many algorithms, right? That is, there's no need to say a priori that I want node 0 to have data from 0 to 10, node 1 from 10 to 20. Perhaps I can leave it up to the algorithm to send me, not just deposit the data, but also tell me where I can find its element, right? That would make the algorithm basically a lot faster in practice because it can actually choose the best way to actually leave the data in the end. And finally, it's tempting to also reverse the question. And instead of ask, what's a data processing plan for a topology? To do the reverse and say, given what we can do in data processing, can we maybe go to the cloud providers and recommend a topology that is more efficient for data processing tasks? And the interesting thing here is basically cost efficiency, right? Sure, what's the most efficient topology? A uniform network, super fast bandwidth everywhere on Earth. That's what's going to happen. But what is the most cost-effective, basically, topology that they can build and we can actually rely on for data processing, right? That's another tantalizing question. With that, I'm almost out of time. So I want to talk about RDMOs, but I will condense this part and go through it really quickly. I don't have a lot of answers anyway. I just want to introduce the questions, but this is very well in line with what the previous talk did. But going through this in maybe just like a few minutes, we are really targeting the problem there of basically now, how do we basically do basically computation at a lower level, right? That is, how can we basically talk and think of an RDMA network where we can program data structures that have multiple round trips involved, right? Interesting questions here that arise basically have to do with first, how did you program against data structures that are remote? And second, simple memory consistent semantics that are very little understood, right? Examples abound. Say I post two requests, R1 and R2. I see R2 completing. Has the first one completed as well? If you connect system A to system B, probably yes. If you follow a much more complicated path, or there is some adaptive routing decision anywhere in your path, this goes back to redundancy and maybe having two links in case one goes down, or having two links to balance performance, the answer is probably not, right? So that's a big difference between me deploying a toy algorithm with two systems connected back to back versus taking something and running at the cloud. The RDMA write, basically, assume I write A or B at an address L. Can I read anything than A and B from this address? And maybe it will become a lot clearer what the answer is if I were to change A and B to the following two strings now. If you answered basically no, well, consider the case of basically you reading which reflects a torn right, where only this part went through, and then I read the older value at the end. This breaks the usual notion of atomicity. Another one, which is by far the favorite, take a local address L. If I were to issue a load for this local address, and then RDMA read, which would send it to the NIC and then give me back the answer in my buffer, will I read the same value? The answer to that is also no. And if you think this is trivial because something may have happened in between, great. But now if I change L to L1 and the other L to L2, and you have some notion of basically sequentiality between the two, which may not hold, right? That's your typical if then else statement, maybe. Then you can see how this becomes basically broken really quickly. And in essence, this goes back to the semantics of atomicity, ordering, and consistency that we seem to take for granted. Well, in fact, they are not basically really considered, right? This is not my work. This is previous work. Actually, I believe Thorsten was one of the authors here that showed that basically, anything is possible from those RDMA operations, including things that are not possible with any known weak consistency model, right? And if you have programmed weak consistency models, the fact that we can see and expose reads that are not conforming to any weak model should make you want to basically, well, I wouldn't say jump out of the window, or maybe it's Europe. Here I can say that, but should basically make you really scared, right?
It's not that deep.
Take Thorsten's advice, who basically, on that, who basically disclaims any liability if the RTL is not working, right? So, awesome. Still, what can we do about it? Basically, let me skip over a few slides here. A simple idea is to actually take those blocks of logic, right? Unwind basically everything, disallow for loops in there, right? And then actually basically manipulate those simple data structures over RDMA requires naturally many basically round trips. Here the classic example is append, right? And I can basically do this as a sequence of read, fetch, then add, and write. Please.
Almost 4 can do it. Move on.
That goes back exactly to the point. Can I do this in one basically step? Yes. And I can actually encode this as what we refer to as an RDMO, right? This single piece of logic that, again, is free of loops, runs in some bounded time, is, if you like, want to think about it, of a certain guaranteed instruction length, right? And we can actually reduce latency in this way. And we have basically come up with some interesting pieces of basically work here where we really want to bridge the gap between issuing sequences of RDMA requests and burning CPU cycles from RPC, right? And we are wondering what is in the middle, right? And we think that RDMO is this layer that basically sits in the middle, right? I don't have a lot of time, and I think a lot of what I'm about to cover has been subsumed in the other talk. So let me skip to the end here. Interesting questions on that part go to basically having a programming model for those user-defined RDMOs. Is it arbitrary code? Is it precompiled or is it interpreted? Do I have a sequence of predefined patterns, right? Think of like maybe the Prism model where it proposed those really simple primitives and a way to continue basically operations from one to the other, right? Finally, a question of balance, right? What does it take to build a balanced system? How much, if I were to run it, do I go with basically something like a DPU, the Bluefield? Do I go lower like an FPGA, right? Which is a great prototyping platform, but it has its own issues with respect to the low clock speed. Or I build main CPUs. Do I go for a cheap one or I go for a top of the line one, right? Interesting questions around system balance. Please.
So just two practical understanding. You said basically the model of RDMA is broken with regard to some of these key properties.
Yes.
So if I build something on top of that, are they also going to be fundamentally broken? So how can I guarantee, like if I cannot guarantee atomicity at that level, then what kind of abstraction would I build on top to guarantee atomicity?
That is, yeah, if you're using something like RDMOs. The answer there is basically in some senses like, think of it as RPC, right? RPC can give you a certain level of guarantee that perhaps, plain RDMA reads and writes cannot give you, right? So in a sense, that is the opportunity to do something slightly better, right? I can take this now as a unit of execution and impose ordering basically constraints. And that is where basically I can do better. An interesting question does arise as I try to mix those RDMOs with regular RDMAs, right? There, obviously, this consistency assumption is broken.